Okay, before we begin on software design though, we need to talk about hardware, particularly storage media, and understand what the properties are of storage media, because they're going to have significant effect on the design of the software we're going to want to build. We want to write software that's going to make this storage media look fast. Now there are major implications of the fact that we're dealing with disks. The most important one is in our programming model. We no longer have a model where we have objects in memory that we can dereference pointers on. Instead, we have an API to get things from the disk. We can read and we can write. And we read and write in units of a page of data, which is a fixed amount of data to and from disk to RAM. So we can read from disk to RAM, and we can write back from RAM to disk. And you can think of a page being like a 32 kilobyte object. So we're going to move these relatively small objects up and down from memory to disk. But we cannot address a particular bit on the disk. We cannot address a particular byte on the disk. In order to address anything on the disk, we have to bring its page into RAM, and then we address location in RAM to read or write the values on that page. Now these API calls to read and write pages are very, very slow relative to CPU speeds. And so we're going to want to plan our reads and writes very carefully. And a lot of what we're going to do in database systems is to make sure that we're reading and writing to the disk exactly when and how we want. Now, this might seem like a drag, this idea that we have to do reads and writes and we can't simply program with objects and pointers and references and all the things we're used to in our programming languages. But sometimes, particularly for data that we care about, having a very explicit API can be a good thing. So for example, if you've ever programmed in C or C++, you know that sometimes you can get a stray pointer and accidentally overwrite parts of memory that you didn't mean to overwrite. Similar things can happen in other programming languages as well. And we want to make sure that we don't mess up our stored data on the disk in the database. And so having to bundle that data up, put it in a page, and then push it down to the disk actually is a form of discipline that prevents certain kinds of errors that we get when we're writing programs. One way to think about it is this. You've probably written a lot of programs. Are they correct? Almost nobody's programs are perfectly correct. But the data that they read and write to the database can be checked more easily because it's going through this simple API. Now let's talk a little bit about the costs of disks and why it is that we might use magnetic disks in this day and age. This is data as of summer 2018, looking to spend about $1,000 at a typical online website. And so here's what you get for $1,000 worth of storage at Newegg, which is an online computer vendor. For a magnetic disk for $1,000, so a hard drive, if you look at sort of enterprise class hard drives, you can get about 40 terabytes for $1,000. If you want a much faster solid state disk, for that same $1,000, you only get 2.3 terabytes. So a factor of over 10, almost 20, a factor of 20 less storage for your money. And if you want to keep your data in RAM for $1,000, you can only get about 80 gigabytes of enterprise RAM. So that's many orders of magnitude less than what you get for magnetic disks. So in terms of storage density, hard drives are still a phenomenal bargain. And that's why they still get used in database systems for very large databases. Now generally, we think of storage as being in a hierarchy. And if you've taken a computer architecture class, you may have seen a figure like this. Things at the top of the hierarchy are small and fast. So the extreme of that being the registers on your CPU. And then things at the bottom are big but slow. So magnetic disks are a good example of that. Now in database land, the database and the logs and backup information are typically stored on disks for very large databases, or even on what's called tertiary storage. So if disks are secondary storage and RAM is primary storage, tertiary storage might be something like a backup service in the cloud or a tape drive. All right, so that's where your database and backup logs are often stored for very big databases. Now, some databases, depending on the deployment, might store their database in a solid-state disk if it fits. So a modest-sized database, it might be worth it to pay more for storage because you get more speed and keep it on an SSD. This would be true, for example, for a database that fits on your laptop. Your laptop these days probably has an SSD, and it's going to be much faster than a magnetic disk. There are, for currently used data, for the data that's hot, we want it to be in RAM. And there are, in fact, databases that fit entirely in RAM. But for the most part in this class, we'll look at more scalable architectures where the database can be in secondary storage like SSD or disk. Now let's look at some numbers. These are fairly recent numbers. An L1 cache reference is about a half a nanosecond to perform. By contrast, go all the way to the bottom. To read a 1 megabyte from a magnetic disk takes something like 20 million nanoseconds. All right, so many orders of magnitude difference. And to give you a flavor of how different these things are, it helps to think about not time, but space. So here's an analogy from Jim Gray, who's a pioneer of relational databases and transactions, and winner of the Turing Award. And he makes the analogy with this: registers are like your head. Okay. By contrast, going to disk is like going to Pluto. Right, that's the timescales we're talking about. If it takes a minute to get something out of your head, and it takes 2 years to get it from Pluto. Okay, so on-chip cache might be in the room, on-board cache in your building. Going to memory might be like going from San Francisco to Sacramento, which is where Jim Gray lived in San Francisco. So that's about a 1.5 hours drive. Going to disk is like going to Pluto. All right, and then of course going to some like cloud service, tape optical robot, whatever, that might be infinitely far away, like Andromeda Galaxy. Okay, so these are the orders of magnitude we're talking about. This gives you a sense of how bad it is to go to disk, or even in a computer, how slow it is to go to RAM. So the regime we're going to be focused on in database systems is that memory to disk boundary, which is the difference between 1.5 hours and 2 years.